We're continuing with the opening chapter of the trigonometry textbook. In this video, we're going to go through the last section of chapter 1, which is titled Using the Definitions of the Trigonometric Functions. Now, I've retitled this video based on what I think is really most important for us to learn from this section, and that's that we really want to hammer home here what is the domain and range of the trig functions. So all of the trig functions, what are valid inputs, and what is the range of outputs. But in this section, we're also going to develop some trig identities. In the opening video, we looked at all the different chapters and sections that we'll be going through in this textbook. And if you remember, in chapter 5 is all about trig identities. However, leading up to chapter 5, we are going to every now and then develop some of these trig identities. So you can see here we're going to talk about reciprocal identities, Pythagorean identities, quotient identities. But then in chapter 5, we're going to go over all of the identities, including we'll talk about these identities again. But again, I think in this section, it's really important that we get very comfortable with the domain and range of all of the trig functions. All right. Identities are equations that are true for all values of the variables for which all expressions are defined. And so you can see that that's why I'm really wanting to put a lot of focus on the domain and range of the trig functions, because even the trig identities, it's all about that these identities are true for the variables for which all expressions are defined. That's the domain of the trig functions. But it's called an identity because if you remember from algebra, what is an identity? An equation that's an identity is you simplify the equation and you end up getting like 0 equals 0. If you kept simplifying, you'd get 2x plus 6 is equal to 2x plus 6. Subtract 2x from both sides, subtract 6 from both sides, you get 0 is equal to 0. It's an identity. It's true for all values of the variable. Same idea here. This is true for all xy pairs. And that's the idea when it comes to trig identities. It's these equations that are true for absolutely any variable that you input into that equation, as long as it's within the domain of the trig functions that are included. All right, so here we're going to develop the first trig identities. These are called the reciprocal identities. And so the definition of a reciprocal is, so like the reciprocal of, it needs to be a non-zero number, is 1 over that number, as long as like x isn't equal to 0. That's a reciprocal. If you have x and x isn't 0, then its reciprocal is 1 over x. So the reciprocal of 2 is 1/2. The reciprocal of 8/11 is 11/8. The definitions of the trigonometric functions in the previous section were written so that that functions in the same column were reciprocals of each other, because sine theta is equal to y over r, and cosecant theta is equal to r over y. Sine theta is equal to 1 over cosecant theta, and cosecant theta is 1 over sine theta, provided that sine theta is not equal to 0. Yeah, so technically, going through the previous section and working the example problems from the previous section, I used the fact that cosecant theta is the reciprocal of sine theta, and we used that. I mentioned that. We used that. But technically, if I was going precisely by the book, we didn't know that those were reciprocals. Okay, like this is technically the first time that the textbook is illustrating this, is pointing this out. But yeah, we could, from the general definition of trig functions, what we could see is that like sine of theta was y over r, and then cosecant was r over y. They're reciprocals. And that's where the reciprocal identities come from. Sine theta is 1 over cosecant theta, and then cosecant theta is 1 over sine theta. You can write it either way. Like sine is the reciprocal of cosecant, and cosecant is the reciprocal of sine. And again, these are all assuming that what you're dividing by isn't equal to 0. And then cosine and secant are reciprocals, and cotangent and tangent are reciprocals. So the reciprocal identities hold for any angle theta that does not lead to a 0 denominator. So here are the reciprocal identities. And what you can think about is that if it's not a quadrantal angle, then you're never dividing by 0 for any of these. It's only at quadrantal angles where the potential for dividing by 0 comes into play, and therefore the identity is it doesn't hold, it's undefined. Okay, they point out here that, so in most cases, the reciprocal of like x, you do this, right? Because anything to the -1 power, that's like a reciprocal, right? But with trig functions, it's kind of a out of the ordinary thing in that, so like if you write this sine to the -1 of x, well, like, okay, we know that, I might not have mentioned this officially, but with trig functions, you have, if we write sine squared of x, what this means is sine of x squared. That's exactly what this means. And you could do the same thing with cubed, etc. And then you also do this applies to any trig function. You could, like, tangent cubed of x is tangent of x cubed. Okay, now it's a little confusing in that, so if you see sine of -1 of x, you would think, well, okay, that means this, which we know is cosecant of x. But this is actually not true. I mean, this is true, but going from here to here is not true. This means that the sine of this is an inverse. So what this is saying is if you have sine of x is equal to y, then sine -1 of y is equal to x. And we're going to learn about inverses in a later chapter. This does not mean reciprocal. So that's just something to keep in mind. It's a little confusing. It's just something to keep. Just remember that. But this does mean, like a power of sine of x. But when it's a -1, that doesn't mean that's a -1 power of sine of x. And there's no, like, also, you might say, well, okay, well, what is this? Is this no, you don't see, you never see like sine to the, or a trig function to a minus power other than like a negative power other than -1 power, which means inverse. You don't see negative powers like this. If you want to write this, then just write this. Or like if you wanted to represent this, either write this or you're going to write this. You don't do this. You only see this form written for -1, which doesn't even mean the -1 power. It means the inverse. So the powers is only for, like, you would do sine cubed x, and that does mean, okay. All right, the reciprocal identities can be written in different forms. For example, sine theta is equal to 1 over cosecant theta is equivalent to cosecant theta is equal to 1 over sine theta. Yeah, you could easily switch. That's why sine is the reciprocal of cosecant, and cosecant is the reciprocal of sine. But you could see that you could also write it like sine theta times cosecant theta is equal to 1. You can write reciprocals in like 3 different forms like this. Okay, using the reciprocal identities, find each function value. Find cosine theta given that secant theta is equal to 5/3. Well, okay, secant theta, that's not the reciprocal of cosine theta. Cosecant is the reciprocal of cosine theta, right? Because you got the co term. No, that's a confusing thing to remember. It's cosecant corresponds to the reciprocal of sine. Therefore, secant it corresponds to the reciprocal of cosine. So secant is the reciprocal of cosine. So cosine theta is going to be 3/5. Just flip it, right? What is 5/3 to the -1? Okay, find sine theta given that cosecant theta is this. So cosecant and sine are reciprocals of one another. So just flip this. You get minus 2 over root 12. But then they're going to want you to rationalize that. So, yeah, there's minus 2 over root 12. So then they multiply. Well, okay, root 12 is 2 root 3. Then they rationalize and get minus root 3 over 3. And we'll work a bunch of examples. Okay, signs and ranges of the trig functions. Okay, so here's what I really want to focus on in this section, the range and even domain of the trig functions. So, all right, when you think about the domain of the trig functions, so based on the general definition, you create that right triangle anywhere. So the domain of the trig functions, if we're not talking about a quadrantal angle, then you could input that angle into any trig function and you're going to get a value. And remember, we're not just going from 0 to 360. We could have negative angles and we could have more than one rotation. So it's literally any number from negative infinity to infinity. Any number. If it's not a quadrantal angle, then for every single trig function, it's going to be an input that results in an output. So, even with the trig functions being reciprocals of one another, some of them are reciprocals of one another. It doesn't matter. If it's not a quadrantal angle from negative infinity to infinity, if the number is not a quadrantal angle, so some multiple of 90, you could say, some integer multiple of 90, right? Because even like 180 is a multiple of 90, 270 is a multiple of 90, 360 is a multiple of 90. If it's not a quadrantal angle, then it's going to be, you input it, you get an output. Okay? It's only at the quadrantal angles where domain issues come into play. And the reason is because at quadrantal angles, one of the sides on the right triangle becomes 0. If you're approaching the vertical from the positive or the negative vertical, it's the x value is going to 0. If you're approaching the horizontal, the negative or the positive horizontal, it's the y value that's going to 0. And so whatever trig function has the y or the x value in the denominator, depending on what the quadrantal angle is going to be undefined. But other than that, if you're not dividing by 0 at a quadrantal angle, then you're going to be defined. And so, one thing you can note just to help you try and memorize this is the only reason you have an undefined issue with trig functions is dividing by 0. There's some functions that you have discontinuities. There's different reasons why functions can be undefined. But with trig functions, it's strictly dividing by 0 because at certain quadrantal angles, the right triangle side becomes 0. The vertical, the x becomes 0 when you're approaching the horizontal, the y value becomes 0. And then since the trig functions are like ratios of side lengths, well, then you might be dividing by 0 in those cases. But if you're not at a quadrantal angle, then all 3 side lengths of the triangle are non-zero. So that's why you never have an issue with not being undefined. Like the radius is always non-zero, even at quadrantal angles. It's only one of the side lengths of the triangles becomes 0 at a quadrantal angle. Okay, and then just don't forget, you're not limited to 0 to 360. You could go from negative infinity to infinity. You can go however many rotations in the positive or negative direction you want. Infinitely many rotations. But with coterminal angles having the same trig function values, though. Right? It's infinitely many rotations, but if you have coterminal angles, those are going to have the exact same trig function values. All right, it says, in the definitions of the trigonometric functions, r is the distance from the origin to the point x, y. This distance is undirected, so r is greater than 0. If we choose a point x, y in quadrant 1, then both x and y will be positive, and the values of all 6 trig functions will be positive. A point x, y in quadrant 2 satisfies x is less than 0, y is greater than 0. This makes the values of sine and cosecant positive for quadrant 2 angles, while the other 4 functions take on negative values. Similar results can be obtained for the other quadrants. The important information is summed here. So yeah, we don't need to, you don't need to memorize this, and we're not going to go over this in too much detail. We got a lot of practice with this in the previous section, in the previous section example problems. But yeah, you know, based on that general definition, what causes a trig function to be positive or negative. It's because the legs of the right triangle that are drawn could be in like the negative x or negative y direction, but the radius is always positive. So depending on, you do use SOHCAHTOA in like an indirect sense, so it just depends on if you have a negative side length, you could have a negative trig function value. It just depends on the quadrant. But you can also notice that you can, if you're just given the quadrant, then that kind of restricts what the value of what the sign of trig functions are going to be, because like in this quadrant, you're going to have a negative x side length and a positive y side length. So you could deduce what the sign of the trig function is going to be, the sign, not the value, the sign. And that's what they do here. So 87 degrees, it says, okay, determine the signs of the trig functions of an angle in standard position with the given measure. So that's an acute angle. All trig functions are positive for acute angles. Why? Because the side lengths of the triangles are all positive. So, and trig functions are just ratios of side lengths. So if they're all positive, you're never going to have a negative trig function value of an acute angle. Okay, 300. So 300 is in the fourth quadrant. So you have, here's the right triangle, or an example of a right triangle that would be drawn. So you've got a positive x here and a negative y here, and this is always positive. And so, yeah, I mean, like you would, you're doing kind of SOHCAHTOA indirectly, where we're talking about like this angle here, right? But then you do SOHCAHTOA with this angle here, but you keep in mind the signs. So, okay, opposite over adjacent. So tangent's going to be negative, but then cotangent will also be negative, like, because the reciprocal of anything is going to have the same sign. If you think about it, anything that's like the reciprocal of something else is going to have this. They're both going to have the same sign. Okay, so opposite over hypotenuse, that sign, that's going to be negative. Adjacent over hypotenuse is going to be positive. So yeah, that's the idea. Okay, negative 200 is, so, okay, 180, and then you just go 20 degrees, so you're like around here. So you've got in quadrant 2, so you've got a negative x, positive y, positive hypotenuse, and so you just do the same thing. Right? This is the angle, but you come to this angle and do the SOHCAHTOA, which honoring the signs. So adjacent over hypotenuse, that's cosine's negative. So then the inverse, or the reciprocal of cosine would be secant's going to be negative. Opposite of hypotenuse, sine, that's positive. So then cosecant's going to be positive. Opposite of adjacent is negative, so tangent and cotangent are going to be negative. Because numbers that are reciprocals always have the same sign, the sign of a function value automatically determines the sign of the reciprocal function value. Exactly. Identifying the quadrant of an angle. Identify the quadrant or possible quadrants of an angle theta that satisfies the given conditions. So sine of theta is positive, tangent theta is negative. Can we identify the quadrant in that case? Well, okay. All this might seem like trivial examples, like pointless examples to do these problems, but the more of these you work, the more the intuition for trig functions gets like steered into your brain. So work these problems. All right. So sine of theta is opposite over hypotenuse. Okay. So opposite, if you think about it, what is opposite for any right triangle that we draw? Opposite will always be the y value. No matter what quadrant we're in, the way we draw the right triangle, opposite, based on the angle of the right triangle that has vertex at the origin, is always the y value. Okay? Now, the hypotenuse is always positive, so what this means is that we're going to have a positive y value if sine of theta is positive. So we're in quadrant 1 or quadrant 2 because that's where y is positive. Okay, now if tangent theta is negative, but we're restricted to these two quadrants, so the only way tangent could be negative is you need, because tangent is opposite over adjacent, you need the x to be negative, so we're in quadrant 2 then. All right, cosine of theta is negative, so that means that that's adjacent over hypotenuse. Hypotenuse is always positive, so when you're in, that means that the x needs to be negative, so we're in quadrant 2 or quadrant 3. It's the only quadrants where the x is negative. Now, secant is what? That's the reciprocal of cosine, and for that to be negative, secant will always be negative if cosine is negative. So actually, we haven't gotten any extra information here. This requirement just automatically made this a requirement. Like here, we had sine theta is greater than 0, but that didn't mean that tangent theta had to be less than 0. This was like an additional constraint. Here, these are like redundant. Like adding this is redundant because this fixes this, so we don't know if it's 2 or 3. Okay, so we've talked about the domain of the trig functions. Now let's think about the range. So the possible outputs. Okay, so let's start with sine and cosine. So they give an example here when we're going from, like, we're in the first quadrant and we're approaching the vertical. And so when you think about sine, it's opposite over hypotenuse, so it's always the y value of the triangle divided by the radius. Okay, now we can obviously pick whatever radius we want, but the triangles are always similar. So it's not like you can't say, I'm going to pick a large radius that's going to be greater than the magnitude of the y value. No, the hypotenuse of a right triangle is always greater than the sides, the side lengths, right? So if we think about the radius just being constant as we approach the vertical, the y value is always less than the radius. Or even if when we approach the horizontal, y is going to 0, but no matter what, in this first quadrant, the y value is always less than the radius, and only the y value is 0 here at the horizontal, but at the vertical, the y value actually equals the radius, but it never is larger than the radius. Now, okay, what about when you go past the vertical? Well, then the y value starts getting smaller again, and then goes all the way down to 0. And then when you go into the third quadrant, it's the same pattern, except now the y is negative, though. The radius is always positive, but the y is negative, and then the y becomes equal to the radius, the magnitude at least, at this vertical, and then it starts shrinking again down to 0. But we're dividing for sine. We're always dividing for any quadrant. We're dividing the vertical by the radius. But for a right triangle, the hypotenuse will never be smaller than any of the legs, and so so this is a leg, right? So what you can see is that the sine and the cosine, because this cosine is very similar. It's the ratio of this leg, of the other leg, and the hypotenuse. You can see is that so cosine is the exact same pattern, just except for the horizontal leg. Cosine and sine will never be greater than 1. No matter what r you pick, you could pick a huge r, or you could try and make y or x as large as you want. Well, it doesn't matter. They're never going to be greater than r. Only at certain quadrantal angles are they equal to r. Okay? So sine and cosine can never be greater than 1. They could only be equal to 1 at certain quadrantal angles. Now, they can be equal to 0 because you could have, like, y is equal to 0 divided by r at the horizontal, and you could have x is equal to 0 divided by r at the vertical. They can be equal to 0, but they can also be less than 0 because in certain quadrants you have a negative x or a y value divided by the r. So, but then they could never go less than -1, right? You can never have a negative y that's a little bit bigger than the r value, or a negative x that's a little bit bigger than the r value. That never happens. It can only, the farthest it can go is that at certain quadrantal angles, you could have a negative x or a negative y end up being equal to the r value, which is, so that's -1. And so therefore, the range of sine and cosine is -1 to +1, including -1 and 1. So like the closed interval from -1 to 1, that is the range of sine and cosine. Okay, now, but what about the domain of sine and cosine? You might be tempted to think, well, okay, every trig function is going to have there's going to be some point where you're dividing by 0, because they're all like, they all are reciprocals of one another, and you can divide by 0 in certain situations. Well, actually, with sine and cosine, there's never a case where you divide by 0. And the reason for this is that, remember, it's only the side lengths that in certain situations, at certain quadrantal angles, the side lengths of the triangle, the right triangle, in certain situations become 0. In certain situations, x is going to be equal to 0 or y is going to be equal to 0. R is never equal to 0. It's never negative, and it's never equal to 0 for any angle. Well, that's with sine and cosine, you're dividing by r. And so that's why with sine and cosine, the domain is all real numbers from -infinity to infinity. There's no value you can plug in to sine or cosine, and it doesn't exist. You're dividing by 0. Okay, now what about tangent? So we talked about the domain of tangent, and so when you're thinking about opposite over adjacent, well, for any triangle in any quadrant, the adjacent is going to be the x, and the opposite is going to be the y. Depending on the quadrant, depends on if y is positive or negative, or x is positive or negative. So it's only when x becomes 0 that tangent is undefined. Well, x becomes 0 at the positive or the negative vertical, so 90 or 270. So tangent you can't input any of the vertical angles into tangent, but everything else is fine. So at the horizontal, tangent is going to be equal to 0 because y is 0, and x is the magnitude of the r value, either positive or negative r. Okay, so that's the domain of tangent. But what about the range? Well, okay, if we let's start at 0 degrees and then go up into the acute angles. So at 0 degrees, y is 0 and x is positive r, so tangent is 0. And then as you increase, what's happening? Well, as you increase the angle, x is shrinking. X is going to, all the way to 90, x is going to shrink towards 0. X starts at positive r, and then it shrinks all the way till theta gets to 90, and then y becomes equal to r. Y increases from 0 to r, x shrinks from r to 0. So tangent theta, if theta is acute, you're going from, you start at, so opposite over hypotenuse, and then you, this is at theta is equal to, this is at theta is equal to 0, this is 0. And then you go to r over 0 at theta is equal to 90. This isn't opposite, this is 0. Well, okay, you can see that you're going from 0 to positive infinity. So going from 0 to 90, you can get any value out of tangent, any positive value, or 0. Now, what about the negative values? Well, we could do a similar analysis in the other quadrants and see that you could get also any value from 0 to negative infinity for tangent. So the range of tangent is all real numbers. So that's a big difference. We went from sine and cosine having ranges from -1 to 1 inclusive, to tangent having range from -infinity to infinity. And then with tangent, the domain, you just can't input like a 90 degrees or 270 degrees, or any kind of multiple, or any angle that's coterminal with one of those. Okay, now thinking about the reciprocal trig functions, we can stick with tangent at the moment. So cotangent, you can think about, is the domain is going to be, you can't input any of the horizontal angles, so like 180 or 360 or any angle coterminal with those, because you're dividing by 0, but it's going to be but cotangent, the range, is going to be all real numbers. For the exact same reasons that we just did for tangent, it's going to be the exact same idea with cotangent, except it's just like, kind of like reversed as far as you're approaching. You start at 0 at the vertical, and then you approach positive or negative infinity going to the horizontal. All right, now what about secant and cosecant, the ranges? Well, and the domains. So, yeah, with secant and cosecant, the difference is, so the reciprocal, you've got like, so secant, that's the reciprocal of cosine. So, well, let's start with sine. So cosecant is the reciprocal of sine. So that's going to be not y divided by r, but r divided by y. So in that case, we can't divide by 0. Y becomes 0 at the horizontal, so you can't input an angle that's like a 180 or 360 degree angle or coterminal with that, where the y is 0. And similar idea for the domain of secant, it's going to be, you can't input a vertical angle because x can't, because it's r divided by x. Now, what about the ranges of cosecant and secant? Seems like it might be all real numbers, kind of like tangent, right? Well, okay, let's think about cosecant. We can start at, let's start at the vertical here. So r divided by y is what at the vertical here? That's positive 1. Then as we come down in this direction, what happens? R is not changing, but y is getting smaller and smaller and smaller to where you go from 1 to positive 1 to infinity, to positive infinity as you approach the horizontal. That's interesting, right? If we're coming in this direction, what happens? Well, y, you go from 1, we're talking about cosecant, so the reciprocal of sine, so you go from cosecant is equal to 1, and you approach positive infinity. Now, coming in this direction, you're going from, so y is getting, yeah, this is confusing because, okay, we go to positive infinity here, but then what happens right when it's undefined at the horizontal, but then when we cross over, what happens? Well, then you've got a tiny y value, but it's negative. And so it's r divided by a tiny, tiny negative y value. That's negative infinity. And then when you get to the vertical, you get r divided by y, which is minus r. So negative 1. So what you can see is that the range of cosecant is going to be negative infinity to negative 1, including negative 1, in union with 1, including 1, to infinity. And if we did secant, it would be, we'd get the exact same range. Okay, so this is really important for your intuition of trig functions, to really get a sense of the domain and range of each trig function and how we just figured that out. So if you need, pause and rewind this, once we got to this point, and we just really went through in detail the domain and range of each trig function. And this is really important for your intuition of trig functions, so make sure you understood this. Okay, so here they give a summary of these ranges. So now here's some example problems related to understanding the ranges, and we're going to work a bunch of example problems. Okay, it says the 6 trigonometric functions are defined in terms of x, y, and r, where the Pythagorean theorem shows that r squared is equal to x squared plus y squared, and r is greater than 0. With these relationships, knowing the value of any one function and the quadrant in which the angle lies makes it possible to find the values of the other trigonometric functions. Yeah, so if you really understand this general definition, if you've been following along and working the example problems up to this point, then you can be given certain information, and then it allows you to find all kinds of other information. Like you only need a certain amount of information about the angle or certain trig functions to then deduce what all the other trig functions are. And again, we'll work example problems that illustrate this. Finding all function values given one value and the quadrant. Yeah, so that's what they're talking about here. And we're not going to go through this example, but we'll work examples and you'll get a feel for what they're talking about. If you have a trig function value, and then you know the quadrant, well then you know what the signs of the trig functions must be, right? You know that the radius is always positive. You know the domains and the ranges. So you could just use your understanding to where all you know is that you're in quadrant 2 and what the sine of theta is, and with that you can get all the other trig function values. And so I'm not going to go through this example here, but we'll work examples just like this in the next video. Okay, Pythagorean identities. So we're going to do some more trig identities. Earlier in the video we did the reciprocal identities. So now they're going to derive some more trig identities. So, okay, here's the Pythagorean theorem. X squared plus y squared is equal to r squared. Divide the entire equation by r squared. Simplify and you get this. Well, x divided by r is cosine theta. Y divided by r is sine theta. So you get cosine squared theta plus sine squared theta is equal to 1. So there's a trig identity. The relation between sine and cosine. Now, you might be confused by this. And so just remember that the way that the trig functions are set up, the definition, it's set up to where this equation, x squared plus y squared is equal to r squared, even if we're not thinking about the definition of trig functions, right? If let's say we forget about the definition of trig functions, this equation, it holds, right? You can think about in any quadrant, you can think about the distance between a point and the origin is equal to this, right? And then so when they divide both sides by r and they simplify to get this, if we're just thinking about forgetting about trig function definitions, this, for any x, y in the plane, x could be negative, y could be negative, right? But the way trig functions are defined, that's okay. We don't violate any of the Cartesian plane rules. So like what I mean by that is, I've talked about how we could, if we wanted to, we could define trig functions to be, you set up the right triangle, but then you think about the legs are the side lengths of a triangle. So legs of triangles are always positive. So you don't think about this as like a negative x. This is always positive. We could define it that way. You could define it however you want. But if we defined it that way to where like the sine of this angle is, or the cosine of this angle is adjacent over hypotenuse, but you think of these as the lengths of the legs of a right triangle, so this is still positive, that's fine. But then you couldn't do this because we made an equation here that, like, you have to restrict the values of x and y to be only positive values, something like that. Well, if we're going to, for this in complete general, for any x or y, in all real numbers, the trig functions are defined to where you can just take this x divided by r for any x. X can be any real number, y can be any real number, and just say that's equal to cosine theta. This is equal to sine theta. Okay, so there you go. There's a trig identity. It's a Pythagorean identity. All right, so now they again start with the Pythagorean theorem, divide through by x squared, and get this. And so y over x is tangent theta, r over x is secant theta. And so here's another trig identity. It's a Pythagorean identity. Similarly, dividing through by y squared leads to this trig identity. These three identities are the Pythagorean identities because the original equation that led to them was the Pythagorean theorem. All right, so here are the Pythagorean identities, and they're valid for all angles for which the function values are defined. So if we come back, like, what they mean by that is, so, here we divided by x squared. Well, x can be 0 in certain cases, right? So obviously you can't that means there's going to be certain values where this isn't going to work, because x, it could potentially be 0 in certain cases, but here r is never 0. So with this trig identity, you can input any theta and there's not going to be an issue. But if x isn't equal to 0, then these two trig identities are completely valid, right? As long as x isn't equal to 0. Okay, we give only one form of each identity. However, algebraic transformations produce equivalent forms. For example, by subtracting sine squared theta from both sides of sine squared theta plus cosine squared theta is equal to 1, we obtain an equivalent identity. Yeah, so you can manipulate these, right, and make other identities. Like you could say that, so sine theta is 1 over cosecant theta, so you could change that and create a relation between cosecant and cosine, right? So it says it's important to be able to transform these identities quickly and to recognize their equivalent forms. Yeah, you can play with these. Okay, quotient identities. Here's more trig identities. Consider the quotient of the function sine theta and cosine theta. So sine theta over cosine theta is y over r divided by x over r, and that simplifies to y over x. That's tangent theta. So there we go. Sine theta divided by cosine theta is equal to tangent theta. Similarly, cosine theta over sine theta is equal to cotangent theta, right? Of course. The reciprocal of tangent is cotangent, so you just flip this, cosine theta over sine theta. Thus, we have the quotient identities. For all angles theta for which the denominators are not 0, the following identities hold. Here are the quotient identities. All right, using identities to find function values, it says find sine theta and tangent theta given that cosine theta is equal to minus root 3 over 4, and sine theta is greater than 0. So start with the Pythagorean identity that includes cosine. So here we go. And so you plug in cosine, and you get sine squared theta is equal to 13 over 16. Take the square root of both sides, but now you have a plus or minus here. But it told us that sine theta is positive. It needed to tell us that, so we choose the positive. All right, so then we can find tangent theta with sine theta over cosine theta, and then you can get the other trig identities with they're just reciprocals. You have sine theta, you have cosine theta, you have tangent theta. Just take the reciprocals to get the other trig functions. Okay, so here's another example of using identities to find function values. We're going to work a bunch of examples just like this. So let's get started with example problems.